Hi everyone! In this video we're going to see a second application of factoring prime numbers, and it's when we have to add fractions together. So let's try and add the fractions 5 divided by 6 and 7 divided by 4 together, but let's first reason a bit on what we actually have to do. For example, if I would like to add 2 apples and 4 apples together, well, that's of course just 6 apples, right? That's easy. But what if I would like to add 2 apples to 4, let's say, bananas? Well, they're not the same. An apple is something different as a banana, so actually I cannot really add them together. What we can do, of course, if we can generalize, both are, of course, fruits. So if you like to say this is 2 fruits plus 4 fruits, then it's indeed these are 6 pieces of fruit. That's what we can do, and it's a bit the same what we want to do with fractions, because, well, 5 divided by 6 is exactly the same as 1 divided by 6, and doing this 5 times plus, and for 7 out of 4, this is 7 times 1 out of 4. So we are trying to add a number of times 1/6 plus a number of times 1/4, but they're not the same, so cannot really do anything, right? So the idea is to change these representations so that we do get something which is the same, like we did for apples and bananas. If we say, okay, these are pieces of fruit, so we can add them together. And if you're actually just calculating in the natural numbers, if you're adding 2 whole numbers, positive whole numbers together, you've actually been doing the same thing, because 5 is just 5 fingers, 5 times 1, plus 7 is 7 times 1, and the ones are the same, so we can just do 12 times 1, which is 12. Of course, we're never going to write these ones. This is implicit, but this is actually behind everything. So remember from last video that, well, there are multiple representations of a fraction. In the last video we tried to look for the best one, but here we actually have to go the other way around. We have to enlarge the numbers again. So we're actually looking for a number which we can form from a 6 and from a 4. And which are these numbers? These are, of course, the multiples of 6. So we're actually looking for the smallest common multiple of 6 and 4, and we will write this as an SCM of 6 and 4. This is equal to what? And so, of course, we're going to use prime factorization to calculate this one, but there is a naive way to do this, and this works for small numbers. You can just start to write down like the multiples of 4, and this is 0. 0 is always a multiple, because 0 is 0 times 4, and then 4 and 8 and 12 and 16 and so on. We can start doing that for 6, 0, 6, 12. So 12 appears in both lists, because these are the multiples, and it's the smallest one. Forget about the 0, because 0 can never be a denominator. So this is just 12. This works, but if your numbers become very big, this can be kind of annoying. So what we can also do is just factorize these numbers, which we will always do. So 4 is 2 times 2, 6 is 2 times 3. So we can read that 2 is the greatest common divisor, but what we actually want to do is, okay, which numbers do we have, which prime factors do we have to add to this list so that we get all of the ones from 6? So the 2 is already there, but we miss 3, so we have to multiply this times 3. And the same for 6, there is already a 2, but in 4 there are 2 2s, so I have to multiply again with a 2. And then I can easily see that the smallest common multiple of 6 and 4 is just, well, for example, 4 times, what did I add it? That's 3, which is 12. And what we can do then is 5 times 1/6 plus 7 times 1/4. So I'm going to write 1/6 as the fraction with denominator 12. And how did I go from 6 to 12? Well, I multiplied with 2, so I have to multiply the denominator also with 2. I do the same for 4. I go from 4 to 12. I multiply it by 3, so I have to multiply the denominator as well, 3. And now I can write this again. 5 times 2 is 10 times 1/12 plus 21 times 1/12. And with our trick, I now see that I'm adding the same things to each other. So I can write this as 10 plus 21 out of 12, which is 31 out of 12, which I can no longer reduce because the prime factors of the denominator are 3 and 2, and they do not divide 31. Of course, I'm never going to do all these intermediary steps, but this is really just to show why we actually have to change the denominators so that they match before we can actually add them together. We're going to do this often just in one go. We're going to see, aha, we're going to calculate the greatest common divisor of 6 and 4 is 12. And then I needed to multiply with 2 here. And I needed to multiply with 3 to get from 4 to 12. And that's it. One final remark here. Of course, what you can always do, whatever will work, is a common multiple of the denominators. And always, you can always find a common multiple by just multiplying 6 and 4. Right? So you can also do, well, this equals 5 times 4 plus 7 times 6 divided by 6 times 4. But you can see here that with a little of additional work here, because these numbers were easy to factorize, our numbers that we actually have to calculate with are smaller. So this also works. I mean, this is just 20 plus 42. 20 plus 42 is 62 divided by 6 times 4, which is 24. But then you see there is a common divisor of 2, which is 31 out of 12. Maybe in this example, the difference is of course not so big, but for certain numbers, it can actually be that using prime factorization to calculate the smallest common multiple will really reduce the amount of calculations you have to do. The next exercise, it's time to test yourself. Bye.